So we've been talking about nuclear reactions, nuclear transformations. I've hinted at these things can be used for bombs and for energy, but there's a lot of fear around the health effects of radioactivity. And so that's today's lecture is talking about using radionuclides in medicine and also the health effects of radiation. So this is a typical exposure that we all get just from our environment of radioactive doses. And remember that the units for radioactivity were all over the place. There were units associated with the particular nucleus or the substance, like the number of disintegrations per second or whatever that are actually happening in the nucleus. Then there were detector measurements like counts per second. So that's just how many times the little detector clicks, and counts per second is another thing. And what's really important health-wise is how much of that radiation can be absorbed by the body. So German scientist Röntgen is the one that discovered the X-ray, and so he got the name for the radiation dose thing, or Röntgen. And this EM is back in the day, they said, what's the equivalent dose for man, like a human body? So if you're standing next to a radioactive object, how much of that radioactivity can be absorbed by the body? So that's what REM stands for, Röntgen Equivalent Man Dose. So ROENTGEN. So Röntgen's the guy's name. E stands for equivalent. Man dose. I put man in quotes because it's human. Okay. And then this M in front of it is milli. Okay, so this right here is milli. So 10 to the minus 3. So these are pretty small doses. We'll see later on what the health effects levels are, but these are our background radiation doses. So the sun is a nuclear fusion furnace. If those nuclear fusion reactions happen close enough to the surface of the sun, when the particles come streaming out of those reactions, some of them escape the gravity of the sun. And so there's a solar wind. They're just charged particles, protons, neutrons, alpha particles, beta particles, neutrons flying out of the sun constantly. And that's what we call solar wind. And it's also called cosmic rays. These are happening from, distant supernova that have exploded in our galaxy and just sent all of their debris out into the galaxy in a straight line, and then they steer around the gravity and so on. And some of those are what cause our cancers. I mean, whole oxygen nuclei from a supernova are flying through space, and they will go right through the walls and right through your body and right through the earth. I mean, they're going so fast and have so much energy. Eventually they slow down and get captured and become an oxygen atom. But when they travel through your body, they wreak havoc. Because if you think an oxygen nucleus is charged 8+, that's a really strongly charged particle. And it can leave, like instead of a cloud chamber, it can go through your body and create a little trail of ions. And so that's part of our radiation exposure. And people that fly a lot, like pilots, flight attendants, people in business internationally that are flying, they have a higher exposure rate because they're flying above much of the atmosphere. This hit close to home. My brother-in-law is a businessman, did international tax law, flew all over the world, and he came down with brain cancer. And so was that related to his, being up above most of the atmosphere for a lot of his job? Could be. You never really know. And so a lot of our cancers do occur from radioactivity, probably. But it's very difficult to, tie down the cause. We also have some genetic susceptibilities. So we'll talk about cancer a little bit more later. Then Earth. So the elements that are in the Earth, many of those are radioactive. So we get 47 millirem per year from that. Some of those substances are made into brick and concrete. We even have radioactive nuclides in our human body. So we have radioactive potassium. Potassium-40 is radioactive. We have carbon-14 because we've eaten plants that have respired the carbon-14 CO2 that came from the upper atmosphere. And then some of that carbon-14 and CO2 is in the atmosphere, so we get some small doses from the atmosphere. And so this is all our natural doses. So we get 126 millirem per year just from natural things. Now, human sources, if you have a medical x-ray procedure, that can give you quite a dose. A single x-ray doesn't give you very much, but if you have like a heart catheterization, they go up. It's really quite amazing. They send this little catheter up through a really large, let's see, it might be a vein. Is it a vein or an artery? Artery. So they go up to the artery in your leg all the way up into your heart, and they have this little thing that spits out contrast agent. And they're taking a motion picture of your body with x-rays. So think about how many x-rays you're getting. They're actually imaging your heart with x-rays at I don't know how many frames per second, but then they're looking at the blood flow through your coronary arteries. So that would be the highest sort of medical x-ray procedure. You get the largest dose for that. Radiotherapy would be if you had cancer and you were treating it with radioactive seeds. Sometimes for prostate cancer, they can put radioactive seeds, these little capsules that have radium in there, and they embed them in the cancerous tumor and shrink the tumor from within. And so then nuclear power, this would probably be from the fuel processing, and preparing the fuel. There's almost no detectable radioactivity coming from a nuclear power plant. It's down at the baseline levels because it's so shielded. And we'll look at nuclear power on Monday. So don't miss Monday. I know it's a holiday week, but we're talking about nuclear power on Monday, the safety of nuclear power, and what we do with the waste, and comparing that to fossil fuels and other kinds of renewables. So Monday's going to be great. So I'd love to see you here. Then electronics and waste. Again, not necessarily nuclear waste, but maybe some nuclear waste. And then radioactive fallout from the testing. So we tested our country probably over 1,000 nuclear weapons. Britain tested some, France tested some, the Soviet Union, China, North Korea, Pakistan, India. All of these different countries have nuclear weapons. They've all tested them in the environment. And this is a small amount of radioactivity that's still somewhere up in the atmosphere. Occasionally you have some radioactive fallout from these tests. That's dropped off quite a bit. So human activity gives us 67 millirem. So it still hasn't even come up to the natural sources. And then if you live in a radioactive area like that has a lot of uranium in the soil, you're going to have a large amount of radon in your local environment. And so that can add almost double the amount of millirem per year. So we live in a radioactive world. What does this radiation do to us? Well, the alpha particles don't really do much to us because we're surrounded by armor. And it's not a very thick armor, but it's thick enough to stop alpha particles. So it hits the protein shell that we have and causes a reaction in the protein shell, but it's not a big deal because we're covered in dead skin cells. So the alpha particles are stopped by our skin. They're really bad if you ingest them because we don't have that protection inside our bodies. So you breathe them in or ingest them, then you've got a problem, probably like 20 times more damage from an alpha particle ingested than a beta particle, because it's that helium nucleus. And if something that's spitting out an alpha particle is creating another daughter element that's also probably radioactive. So there's a lot of damage that can happen with the alpha emitters. Beta particles will go through our protective coating and get into our dermis and then a little deeper into our tissues. And then gamma rays can go right through us. So they can create some damage on the way if they're absorbed, but most of the time they just travel through us. So it's really the beta irradiators and ingested alpha emitters that are the real problem. And of course, rapidly dividing cells are affected the most because they're in the process of duplicating the DNA more frequently. And when you wreck that sequence of duplication, then you can create mutations and you can have cells that have a runaway cycle, like a cancer cell. Most of the time, you damage the cell and it creates such a defective cell that it doesn't express the right proteins on the surface or it doesn't function correctly, and your body's immune system identifies that cell and says, we got to get rid of this one. So they'll destroy that cell, metabolize all the parts, reuse them in other cells. But there's a small chance that that cell could become cancerous. So it's really a statistics game. But if you have young children or children in utero who are building lots and lots of tissues, they're the most susceptible to radiation damage. Because we live in this radioactive world, we have, again, some ability to call out damaged cells. Now, electromagnetic radiation is technically radiation, but we use this extra term ionizing radiation. So this is the real thing that we should be careful with. And so when they talk about microwave radiation, that's not ionizing. That's pretty low energy light. And so, yeah, microwaves might be bad for you in terms of standing too close to them. My mom always said, don't stand so close to that microwave. It wasn't because of ionizing radiation, but if it does leak microwave radiation, it might heat up, I don't know what, that's fluid in my eye. I don't know what is going to happen with that. But microwaves are not dangerous. They don't put out ionizing radiation. The energy has to be above 1,200 kilojoules per mole, which is the first ionization energy of water. And we're 70% water. So if we ionize water in our body, it's going to create reactions that we don't want to happen. And so this hydroxyl radical is an interesting thing. So let's think about all the things that we have. We have water. We have hydronium ion. We'll just do H3O plus. We have OH minus, right? We've seen all of these things so far. This is a brand new thing. This is called hydroxyl radical. OH, and it's just got a dot. Okay. Let's see, I probably need...
It doesn't have a charge?
Yeah, no charge. So it's got that extra electron.
Oh, no.
Yeah, so it's a very reactive species because it has this extra electron right there. So a lot of times they just draw it like this, OH dot. So it's as if, that radiation came in and it broke this bond. And so one electron went on the hydrogen, one electron went on the oxygen, and so we have OH dot and H dot. And so now this hydrogen atom, it's not a proton, a hydrogen atom, can attach itself to a double bond, most likely, and start creating polymeric reactions. Free radical polymerization is something that is constantly used in our culture. I mean, we make all of our polymers with 3 mechanisms, and one of those mechanisms is free radical polymerization. So any double bond then can polymerize, and your body's full of molecules that have double bonds. This same thing can happen with oxygen. If you have oxygen molecule, in reality, there's like a diradical in oxygen, and this can take the hydrogen away from water. So this is not as frequent as the radiation damage, but it can happen where then we have OH dot and OH dot. And this right here is one of the first steps in oxidation. And it creates damage in your cells. And so what do we take typically as a supplement so like an anti-aging supplement or for your health? An antioxidant. They stop this, okay? They stop the oxygen from making these free radicals in our body that create all these terrible reactions. And the same thing, if you take an antioxidant, it can help you with radiation damage as well, because radiation damage primarily produces hydroxyl radical, and vitamin C, vitamin E, those kinds of vitamins will protect your body, give you some protection against these free radicals. What will happen is these will react with the antioxidant and not with your cells mechanisms. Okay. So anyway, that's a little plug for antioxidants. However, the toxin is the dose. Don't overdo it. Take a reasonable amount, look at the bottle, follow the instructions. Okay. So let's look at the biological effects of radiation. So this, again, is a dose in rem, not millirem. Okay. Not millirem. Okay. This is rem. So 0 to 25, there's no detectable clinical effects. Once you get above 25 rem, you start to see the body reacting to the radiation dose. You start to see a decrease in white blood cell counts. You get up above 100 to 200, you see nausea and a large, marked means a large decrease in white blood cell count. You get up to 500 rem, that's the LD50. So LD50. So LD50 means death of half the exposed population. It's a statistical term, so that's the level at which we expect half of the exposed population to die. So if this classroom was hit with 500 rem, statistically we would expect half the class to die. Okay. So if you get above that, your chances are really going down fast. Okay. Now, we work with radioactivity all the time in power plants and other facilities. So how do we protect our employees? We wear dosimeters. So dose meters, they're little film badges. And if you're in a radioactive environment, that radiation is exposing the film. And so you keep your film badges probably we had a big board at the beginning or entrance to our building. And so if I was going to a radioactive area, I'd pull my film badge off and stick it on my shirt and go and do whatever work I was doing. And when I came back to the office building, I put my badge back on. And our occupational safety folks, once a month, would come through and pull all those badges down, put all fresh badges up, and then they take our badges and analyze how exposed the film was. And they would tell us our dose that we got the previous month. Okay. Now, if our doses, like in nuclear power plants and so on, if the doses go over half a rem in 3 months, then they're removed from their duties. Doesn't mean they're fired. You can't fire them because there's not anything they did necessarily. It's just they've worked in a radioactive environment. Maybe they're an X-ray tech and they take X-rays every day. And so in order to keep their doses way below any kind of medically damaging dose, they pull them off those duties just to keep their average annual dose at a low rate. At Pantex, it was 0.1 rem per year. So if we got 0.1 rem in a month, we were done with being in a radioactive area for the rest of the year. Okay. I never saw any hits on mine at all. So I take that back. I got one like in the last decimal place. I forget if it's 0.001 millirem or something, but I saw one little tick, 1 month that I was there. And then the overarching policy for keeping employees safe and working with radioactivity is this ALARA technique. And it just means that we keep everything as low as reasonably achievable. So if we have, back in the day in the 60s and 70s, if you're not familiar with Pantex is the place where we do all of the refurbishment and dismantlement of our nuclear stockpile. So all of the nuclear weapons were constructed there, assembled there. They come back there for maintenance. And then when it's time to dismantle them, because of our different treaties that we have to bring our nuclear stockpile down in number, they do the dismantlement there. So there are a lot of radioactive areas where they're working with the nuclear parts. And so I worked there. That's why I put so much into this nuclear part of the course, because that's a bit of expertise that I have. And this as low as reasonably achievable. The guys would tell me back in the 70s when they were working on the weapons, they would have 3 weapons in one bay. And they would work with one and the other, then the other. And it was really efficient. Man, they could really move them through. But that's not as low as reasonably achievable, right? And so they lowered their dose quite a bit by just having one in at a time. It took a little longer, but it was safer, right? In terms of radiation safety and health, that was safer. And so if we could afford to operate that way, then let's operate that way and make it safer for our employees. Another way to enact ALARA is if you have a radioactive workspace, you work there as short a time as possible. And you don't put your coffee and your desk right next to it. So time, distance, and shielding. So you work there as short a time as possible. You keep your distance when you're not working there. And then if you need to, you put up shielding so that it blocks the radiation. And shielding is, well, you get this at the dentist office when you get the x-rays, right? They put the thing in your mouth, the film, and they put that lead apron over you. And so the lead apron is shielding. They give you just a short burst of radioactivity, the x-rays to take the film. And then the worker who's doing this day in and day out is behind a little screen. That's distance and shielding. And so they're obeying ALARA to keep their doses down. Okay, let's look just shortly at the Fukushima reactor disaster that happened a few years ago in Japan. The reactor behaved like it should have. There was an earthquake offshore, and then there was a tidal wave that came. So as soon as the earthquake triggered their seismic detectors, they started shutting down the nuclear power plant. So it went into a shutdown mode. They just decoupled from the generators. And so this is making steam, and then the steam goes out and spins a generator. I'll just draw a little fan here. Okay. So the steam goes through there and spins a fan. Fan spins a generator, which generates electricity. So as soon as they detected there was a problem, they shut down the connection to the steam or to the generator, and then they started cooling the reactor down. They dropped the control rods in to absorb the neutrons and slow things down. But this right up here is the problem. This spent fuel pool. It's kind of hard to say. Spent fuel pool. So it's over here. And after the efficiency of the fuel drops to a certain level, they go ahead and pull those fuel rods out for reprocessing and put fresh fuel in. And so the spent fuel sits in here. It's extremely radioactive because it has a lot of really short half-life elements in it. We let those decay away for several months, and then it's down to a level that's safe to handle, at least robotically. Then they come along with this little crane. They pick the fuel assembly up, drop it down through this tunnel, and there's a train that comes in and gets it. So the train comes in, gets the spent fuel, takes it out to the reprocessing facility. And this is filled with water to keep it cool. And over here they had a generator, a diesel generator. And the tidal wave was this big. Okay, It came in and swamped the diesel generator. That diesel generator recirculated the water to keep that pool cool. And so when the diesel generator went down, it was, and they had engineered this for a tidal wave that was like 5 meters high. It's a pretty big wave, 5 meters. Okay, 15 feet roughly, and it was like 5.5.
Oh. So close.
Missed it by that much, right? And so the circulation water quit. And so then this hot fuel started just evaporating the water. And when the water gets down below the level of the fuel, then you have exposed fuel. And then air does not cool things as well as water. So then that fuel started getting really hot. And right at the surface where there was this super hot zirconium metal and the water was hot enough to come apart and make hydrogen and oxygen. Okay, so then this whole upper area here was filling with 2H2 plus O2, the perfect stoichiometric amount, because it came from water. And it's building up and building up. And they knew this was happening. In fact, one of the buildings had a crack in it because of the earthquake, and they had a fire truck, and they were trying to spray water through that crack to keep that cool. And eventually they realized this isn't gonna work. And so they backed away, and the building exploded. Now, the building's made out of concrete, but this upper area is only made out of steel. And so it was such a perfectly symmetric explosion. I'll probably show it on Monday, that this square roof just went straight up. It's amazing. So that, they knew something was going to happen, so they had the videos on it and everything, and the roof just goes straight up as it blew up. It didn't really damage the rest of the facility because the thing's made out of concrete, and this was just a gas explosion at the very tip top. So it just went boom, blew the top of this roof off. Well, look at all that tubing and everything. That landed somewhere, right? Landed back on the site. And so the workers, this is the thing that really made me mad about this, and made me mad about Katrina, made me mad about Rita, is, I'll say this on camera, the press is the enemy, okay? They lie. And if they're not lying, they're just uninformed. They were saying how the workers at Fukushima's control room were working in their graves, that they were basically helping. Yeah, they were doing great work, right? Trying to get this reactor to cool down, and they're all going to die, you know. And they were calling their parents. They were so distressed and everything like that, when the radiation monitors were not registering lethal doses or anything like that. But they had generated so much fear. And one female worker received 1.7 rem. Remember, the detectable clinical effects kick in at 25 rem. Okay? That's above her limit for the 3 months, okay? 0.5 rem. So she's burned up for most of the year, okay? Medical diagnosis, there was no impact on her health. So they followed her. Her dose meter told them she had 1.5 rem. Radiation controls differ between male and female because of the possibility of an unknown pregnancy, so they measure theirs every 3 months. Now, there were 201 people working at Daiichi and 645 people working at Daini, and no workers went above 25 rem. And the media was just telling everybody, oh, these people are going to die right there in the control room and everything. 30 people went over 10 rem, and here's my source for that. And then, and yet after Fukushima, Germany decided to phase out all of its nuclear power facilities. Yeah, which in my opinion is a ridiculous overreaction. Anyway, now does that mean that this was no big deal? No, this was a big deal. The steam lines under that reactor did crack, and they did leak radioactive primary coolant water into the groundwater. So there is a problem there. Once again, radiation tells you where it is. And so they drill wells around this, and they can follow where the radioactivity is. We have this method of what's called pump and treat. You suck on those wells, and you pump fresh water in upstream, downstream, wherever the groundwater is going to go, and you can funnel the radioactive water towards certain extraction wells, and you just pump it out. You filter it, you put in fresh water. So it's something that's treatable, but it is a problem. It is an environmental release of radioactive water. The fuel itself did not get released into the environment. Okay, so let's talk about the deaths, comparing these different ways of generating power. So this is deaths per 1,000 terawatt hours. Most facilities produce megawatts of power, but if you're dealing with like nationwide or worldwide amounts of energy, then you get up into terawatts and exajoules and so on. And so in coal, again, the mining of the coal with explosives, the transport of the coal, the production of the powdered coal at the power plant and all of that, it's responsible for about 100,000 deaths per 3.6 exajoules. Oil, 36,000, natural gas, 4,000, hydro, 1,400, and nuclear is way down here. So in terms of our global consumption, the global consumption of energy is 425 exajoules per year. So for nuclear, if we were to run the whole world on nuclear, it would be around 10,600 deaths per year. If we ran the whole world on coal, it'd be 11.8 million deaths per year. Incidentally, that's not even really feasible. That's 5 times worse than the Intergovernmental Panel on Climate Change. like coal, like their worst case scenario in terms of amounts of CO2 emitted using the different fossil fuels and so on. Running the whole world on coal would mean no natural gas, no oil, no anything else. And so that's crazy. Natural gas, again, 4,000 per 3.6 would be 472,000 deaths per year. And wind, you think wind, what's wrong with wind? Well, you got to put those things up on the pole, right? That'd be 17,000 deaths per year if we generated every bit of power per year. And COVID, according to Google, gave us 6 million deaths over 2 years-ish. 2.5 years.
So that's up there with
Yeah. So anyway, just talking about different sources of energy. Every source of energy produces some sort of pain, right? Okay, so let's talk about that contamination. That metal that blew off the top of the roof landed back on the power plant site, and some of it was really radioactive. Some of the rubble gave the highest dose of 30 rem per hour. So in one hour, you would have gotten a dose that would have shown clinical effects. Okay, you could take that 30. Well, let's just make it 50, right? If it was 50 and you were there for 10 hours, that's 500 rem. That's a lethal dose. Okay, so you work at 2 8-hour days, hands-on, full 8 hours with that rubble would probably kill you after 2 days.
Jesus.
Yeah. So what do? Well, we get one of these guys right here. This is a dump truck that's there's no guy in there. Okay, RC, radio controlled dump trucks and grapplers. Send in the robots. They put that on the dump truck, and you can go put it in a safe environment. Other debris patches were 3 to 4 rem per hour. At the edges of the site, so at the edges, the fence line, 0.06 rem per hour, 60 millirem per hour. And remember, our background, at least here in Huntsville, is 13 millirem per hour. So it's pretty small. And then some of the water transfer pipes were pretty high too. The levels of the air, they ranged, because it fluctuates, half a rem to 2 rem per hour. So yeah, there was some radionuclides floating around that would settle out. So let's talk about what happens after you receive a radiation dose. On the left is what we would call, I guess, typical toxicology. So doses below the threshold can be handled by the body, okay? And doses are not additive. We'll explain what additive means in a minute. And then this idea of hormesis is another theory that says small doses of radiation are helpful for killing or culling out weak cells. But that's optional. You don't have to believe in hormesis to believe that there's a threshold that the body can handle. And then there's this linear no threshold theory, which is a really extreme theory. It says all doses are detrimental no matter how small. That's one of the principles. And it says that doses are additive, okay, in a linear manner, no threshold. So even the smallest dose is detrimental, and they add up over time in a linear manner. And this played a political role in 1959 to enact the Atmospheric Test Ban Treaty. So between the United States and Russia or Soviet Union, we were going back and forth. Then they detonate 6 bombs in the atmosphere, and we do 8. And then they do 10, and we do 20. And it was just getting out of hand. And so they said, well, look, we're making the whole world toxic because all this radiation is going into the atmosphere. And we wanted to stop them from doing it, and we wanted to stop doing it. And so we really pushed this linear no threshold theory to scare people about radiation. And it worked, and we got the test ban, and so we all started testing underground where the radiation would be sequestered in the soil. But this continued to this day, and we can't get rid of it. This is why people are terrified of radiation. Not general people. General people are terrified by radiation because of the press or just the general media, right? Or consensus. But the people who are, otherwise knowledgeable, who have bought into this linear no threshold theory, think there's something magic about radiation. And really, here's some absurd examples of the linear no threshold theory. Have you ever breathed in automobile exhaust? Walking through the parking lot? Absolutely you have. This linear no threshold theory claims that someday you would go anoxic due to CO poisoning because those additive doses. That's not how it works. Your body processes some of that CO. The toxin is the acute dose. There are such things as chronic effects, but this is saying this is a chronic additive toxicity, and that's not how things work. Same with ever swallowing wrong. You get a little bit of water in your lungs, you cough, cough, cough. The linear no threshold theory would say you will eventually drown because every little bit of water that gets in your lungs stays there forever, right? And then you keep adding to it, and then eventually you can no longer get oxygen. So LNT theory is not how toxicology works. So how does toxicology work? Well, this is the baby toxicology 101. The toxin is the dose. If you overwhelm your body's ability to process the thing, then that is toxic. That's a toxic situation. So you have ADME, absorption, distribution, metabolism, and elimination. So absorption, toxins in, I point kind of towards the mouth, but it could be breathing in, it could be through your eye, it could be through your skin. There's lots of ways of routes of entry. And you have the toxins and normal environmental input. Then those go into the body and they're distributed. So they go around and distributed amongst the body into your tissues, and then your body reacts to them. It metabolizes them or just directly eliminates them through your kidneys or through your gut. So either poop it out or pee it out. If it's water soluble or in the gut, it just stays in the gut. Or if it goes into your bloodstream and it's not necessarily water soluble, it might be metabolized by the liver to make the metabolism products soluble, and then you pee those out. Okay. And so the external exposure to radiation is governed by the time of the exposure, the distance, and the shielding, and then the metabolism rate of any damaged tissue, if you do have some damaged tissue. And that's the thing that we would call radiation sickness. If you build up damaged tissue, it's the swelling, it's the metabolism of those dead cells. And then you eliminate the toxins, the metabolites, and the normal input. So that's toxicology 101. You can throw your body off by doing too much of one thing. In fact, water, there have been people that have died in hazing, like substituting water for alcohol. And they drink too much water, they dilute their bloodstream, and the sodium concentration is too low to maintain their central nervous system, and they die. Okay, so this is that curve that shows the LD50. So if you took a bunch of people or animals, mice, whatever, and you expose them to a particular set of doses, you might have some that, at this dose that nobody dies. Up here, everybody dies. In the middle, you might have, these are up here. Dead. Okay. And then here in the middle, you might have a person down here that gets a big dose but doesn't die. And down here, you might have a person that gets a small dose but dies. And here you got someone that gets 50-50 and doesn't die, and so it starts to get kind of noisy in the middle, right? And so they do this treatment where they figure out what curve best fits these numbers. And they fit that curve, and then this right here is the LD50. So they look at the dose, and they figure out what kind of causes this threshold for whatever effect they're doing. But there are other levels on here too. This FEL is the expected death. No, this is just 50% at LD50, but up here is like an expected death. That's like 95% chance of death. Then down here you have the lowest observed AEL is adverse effect. And then you have this no AEL, so that's no observed adverse effect level. It's probably like 1/3 of the lowest. So you have the lowest observed, and then you probably take 1/3 of that, and then down here you just have no effect at all. So this is the way we treat all of our toxins: water, fentanyl, everything. Okay. And then we have biological half-lives for those toxic substances. If you get them in your body, how long does it take your body to get rid of them? And this is made for industrial safety. So they're saying if you have a worker exposed, say, to mercury, how long can you detect that mercury, right? So this is mercury. It's saying that half of that mercury is gone in about a week. So if I have people working with mercury, let's say all of you guys are filling thermometers with mercury and we're selling thermometers, and I want to make sure that nobody's really exposed to a large amount of mercury, I should test your blood on a week or biweekly basis, because in each week you're going to have lost half of your exposure. So if I test you every Friday, I could still detect that mercury. If I test you once a month, I might not detect an exposure. test on the 31st, and then on the 1st you get exposed, and then the half-life is 1 week. So by the time we get to the next 31st, you're down at like 1/16 of your dose. So it's not good. Some of these things stay with you a while. Look at cadmium. 10 years half-life. That stays with you, doesn't it? And then up here, like some of the solvents, benzene you've heard of. One of these up here, it's not listed because it's not an industrial toxin, but GHB. So gamma butyl hydroxy, let's see, GHB, gamma hydroxy butyrolactone. It's a date rape drug or drug facilitated sexual assault drug, and it's eliminated in hours, like maybe even under an hour. So in order to detect someone who got something put in their drink and then a sexual assault a few hours later, by the time they get to the doctor and give a blood sample, it's probably gone. It's probably been breathed out and peed out. And so that's why it makes that one really hard to prove, right? Because there might be a more stringent charge if you could prove that someone slipped you a drug and took advantage of you. And so that's why a rapid blood sample is really important if we think GHB was involved. What about hypersensitivity and allergies? Now, some toxins do create hypersensitivities, so people can be allergic to tree nuts and peanuts and latex, certain glues like super glue, isocyanates, beryllium oxide. These will trigger the body's immune response, and so it'll be on high alert, and you get a small exposure to them again, and then you have an allergic reaction. And long-term, no adverse effect level doses of substances that accumulate can cause hypersensitivity. So these are very low doses. You don't detect any health effects, but these substances accumulate and create an imprint in your immune response. And so things like cadmium, lead, mercury, polychlorinated biphenyls can do this. And these would be a chronic effect because they accumulate, especially cadmium. And then in terms of cancer, some individuals are not able to metabolize or kill damaged or cancerous cells. And these are the situations where you have really, really young children get leukemia or some sort of cancer. It's because whatever issue with their immune response is that they're not able to identify those cancerous cells and attack them. You guys are much older than that. So every one of you probably has the ability to kill the generic cancer cell. There might be one or two types of cancers that gets through your response because of some genetic thing, but you wouldn't be this old without cancer if you weren't able to kill some cancer cells. Okay? Because cosmic rays and things, we live in a radioactive world. So it's chances that every one of us has had one or two cancer cells and killed it already. Okay? And since there's no real physical way for our body to accumulate radiation, radiation doesn't act like a toxin, it acts like an injury. And I think that's the mindset to have. Radiation isn't toxic, it's injurious, just like a sunburn. The sun is great for you, but too much is injurious and can create problems. And so let's talk about injury to our lungs. Radon is probably the biggest culprit. I showed you this decay path from uranium down to lead. And so once it hits radon, it's now chemically inert, it's a noble gas, it's highly mobile, and it'll percolate through the rock in the soil and even through concrete. And it's trapped in energy efficient homes. And when you breathe it in, if you're unlucky enough to breathe that radon atom into your lungs and it decays while it's in your lungs before you breathe it back out, it's a short window there, right? And then it becomes polonium and lead and bismuth, and you've got all of this left over. So from radon, it goes down, polonium, lead, bismuth, polonium, lead, bismuth, polonium, lead. All of those alphas and betas now are being emitted inside your body. So that's why it's a problem. And so this may have been attributed to 14% of lung cancer deaths. And it's a mystery to me, too, because look at the half-life of radon. The longest half-life is this one right here at 3.8 days. But that shows you the variability in the half-life. That's the half-life. But that means some radons decay right away, and some can take years. So there's a small chance that radon is not decayed yet, makes it up to the atmosphere, and you breathe it in. This is comparing radon's half-life to all the others. We talked about strontium and iodine-131. Let's look at some of the medical breakthroughs in using radioisotope imaging. One of the earlier uses of this was imaging the thyroid. And so the thyroid gland will absorb iodine. And so you could put radioactive iodine in a person's bloodstream, and the thyroid would pick that up, and it would send out, basically emit light. And then you could come along with collimators, a phosphor screen, and light detectors, and you could image that area of the neck. This is the PET scan. And again, we don't have any collimators in a PET scan. What we do have is the positron, let's see, the carbon, like in this case, the carbon 11 is in the body. Let's say this is a cancerous area in the brain, and it's using up sugar preferentially from the tissue around it, and it will glow. And the nice thing is, if you have a cosmic ray coming in and it hits this detector, the computer will say, oh, I got a hit on, detector 5, right? But if there's no simultaneous hit on any of these detectors on the opposite side, it knows it did not come from a positron, because the positron's a 2 gamma process. So every emission of a positron sends out 2 gamma rays. And so those are going to hit the detectors at the same time. So the computer can ignore all of the background noise. And that's what makes this technique so sensitive. And this right here in the middle, this screen is a PET scan. And you see how dark it is. There's very little background noise. But this spot's glowing and this spot's glowing. So there's something going on in those 2 places, right? And if they're looking for cancer, maybe they put a sugar molecule in there, then those are probably 2 cancerous regions. This is a CT scan. And notice the CAT scan, or computer tomography scan, doesn't show those regions at all. There's a little tissue there, but it doesn't show anything special about it. And there's a tissue there, but it doesn't show anything special. So you can't locate the cancer with a CT scan, but you have better contrast of the organs. And so they can combine these 2. And so you can see where the bone structure is, you can see the outlines of the organs, and you can see with sort of false color added in where those cancerous spots are.
What about an MRI?
MRI is really high resolution too. It doesn't use any radiation. The CT scan uses the X-rays, and the PET scan uses the positrons. MRI uses nuclear magnetic resonance, and so it's looking at the spins of the protons in your tissues, and it'll have a really high contrast image.
So which one do you think would be more effective then, or are they kind of the same?
Well, the MRI would be a really high-resolution anomaly detector. Like if something is the wrong shape, then MRI would be the way to go. But as far as like finding a cancer that's voraciously using sugar, then a PET scan would be, because it's going to preferentially absorb that positron emitter if it's put in a sugar molecule. So it's going to glow, whereas the MRI just looks at the structure of the shapes of everything. It won't detect a glow. And they might be able to use some kind of contrast agent, but I'm not sure about that.
Yeah, contrast. Sure.
Yeah. So we'll talk about nuclear fuel on Monday, but I just wanted to show you the internal structure. You have the fuel rods here and the control rods. And so these fuel rods transform into other elements, and some of those are medically useful. And so here's a nuclear reactor that's not made for power. I just want to show you down here. This is the nuclear reactor right here. So down there is the fuel rod assembly. And there's all these little tubes that go down in it, and those tubes are what we call rabbit tubes. It's just like the bank teller. You put your money in the tube, and it goes through the ceiling and over to the bank teller, and then they send it back. We can send samples into a nuclear reactor using the same kind of bank teller thing and irradiate the crap out of it with neutrons and things and transform elements on demand. And so this is how we make a lot of our medical isotopes. And then how we handle them is not like Homer Simpson. Notice he has gloves, and gloves can have holes in them.
Oh.
And we've had people die in the past, in the 50s, 60s, handling radioactivity with gloves. And so now we use these hot cells, which have mechanical manipulators. And so down here is this handle. You've got a couple of handles, and inside you've got kind of robotic hands that you manipulate with these handles. And so you're still doing it. You don't have to program the robot. You're the program. And you're using these manipulators, and you can work with stuff that's really radioactive in these hot cells. So that's how we handle the radioactive materials and keep our workers safe. Okay. See you next time.
Thank you so